Angela Foerster, and as you can see, exactly solve models in the design of quantum architectures. Thanks, Angela.
Okay, so good morning for me, good afternoon for you in Australia. It's an honor for me to have the opportunity to present a talk celebrating the life and achievements of Rodney Baxter. So I thank the organizers, thank you Murray, thank you Vladimir, thank you very much. So as Murray said, I'm going to talk about exactly solved models in the design of quantum architectures. But first of all, I would like to say a few words about Rodney Baxter. We all know he was a pioneer, a founder of our field of integrable models. Just to cite just one example of his classic pioneering work, exact solved model in statistical mechanics, has inspired all of us and continue to influence many generations of researchers. And I would like to share with you how I met Rodney Baxter. I first encountered his work in the 90s during my PhD when my advisor, Mikhail Karayovsky, asked me to read this book before any other discussion. After that, I met him in person in 97 at a conference in Australia, and after that in many conferences, most in Australia. I also had the privilege of joining him for lunches and tea during my sabbatical at the ANU in 2013, everything arranged by Murray Batchelor. After all, I met him again at this series of conferences, Baxter 2015 in Cairns and Baxter 2020 in Canberra. And a few words of what I learned from Rodney Baxter. I can say that his work shaped my approach to theoretical physics. He inspired me to value clarity, relevance, and elegance. And not only this, his quote, "You don't necessarily make progress by thinking all the time. Sometimes you need a sabbatical," also reminds me that stepping back can also lead to insights. His other famous quote here that is written in his book has also guided my research. So we can say that Baxter left us much more than models. He left a way of thinking, and his influence continues to inspire me and many others in the field. Okay, now moving from Baxter's legacy to more modern applications, here I would like to discuss integrable multi-well quantum tunneling models in cold atoms and explore some applications. But why are we studying these integrable tunneling models? So we are studying them because they display high potential for applications in the development of quantum technologies. So these models, they can offer analytical formula and predictions, enabling precise control of quantum states. In addition, they can also offer a platform for studying and manipulating quantum correlations and entanglement. And they also can guide the design of quantum devices. So they are very important. And in my talk, it will be divided in 4 parts. First, I will introduce integrable bosonic quantum tunneling models. And after that, in the second section, as a first application in a static frame, I will show how to use the 4 sites in the ring to generate null states. And in the next section, I will present an application in a rotating frame. I will show how to use the 4-site models in a tetrahedral geometry to construct a quantum turntable. And then I will go to some concluding remarks. Okay, let me begin by introducing you the integrable quantum tunneling models. I will begin with the simplest case from all, which is the case of 2 L's. This is the 2-site Bose-Hubbard Hamiltonian that I will briefly comment here. So we have 2 L's, so we have N1 particles in well 1, N2 particles in well 2. The total number of particles is conserved. We have here the K is the atom-atom interaction term. Delta mu is an external potential that measures the asymmetry between the wells, and epsilon is a coupling for the tunneling of bosons between the wells. So this model, although very simple, it's very physical. It exhibits very interesting physical properties. If we study the quantum dynamics, we will clearly see, for example, tunneling and self-trapping. And more, we can show that this model is integrable, that it can be formulated by the Yang-Baxter equation, and it can be solved exactly by Bethe-Ansatz methods. So in this construction, a key ingredient here is the Yang-Baxter equation. This equation here, which is a sufficient condition for integrability proposed independently and in different contexts by C.N. Yang and Rodney Baxter. This is just one of the many contributions of Rodney Baxter. Okay, now we aim to extend these results to multiple or more wells or sites. The first, the more natural candidate would be the L-site Boss-Hubbard model. However, it's not integrable in general. And in fact, until recently, there was a belief that constructing integrable multi-well systems was not possible. So we solved this issue and found that integrability requires the presence of long-range interactions. And the algebraic constructions of this model is a bit tricky, presenting some challenges to obtain all conserved quantities. So now I want to show you the other models in this family, so the integrable triple well Hamiltonian, the integrable four-well ring, and extend to integrable multi-well tunneling models. So this is the integrable triple well Hamiltonian. So you can see the three wells here again, N1 atoms in well 1, and 2 atoms in well 2, and 3 atoms in well 3 or site 3. The total number of atoms is conserved. So about the parameters, here the parameter U controls on-site and interwell interaction between the atoms. And the parameter T here denotes the coupling for the tunneling of bosons between wells 1, 2, and 2, 3, so neighboring sites. This model is integrable. We can find the Bethe-Ansatz solution, find the Bethe-Ansatz equations. We can find applications for this model. For example, we can construct an atom-tronit switching device. I will not talk about this here, just mentioning it. We have also discussed it for a more general audience. Now I want to go to the integrable four-well ring model. So this is the Hamiltonians. Now we have 4 sites or 4 wells. The notation is basically the same. Again, U controls on-site and interwell interactions. And the T's are the coupling for the tunneling of bosons between wells 1, 2, 2, 3, 3, 4, and 1, 4, so the neighboring sites. Also, this model is integrable. We can also find a Bethe-Ansatz solution. We can find applications, so we will discuss these applications in the next section. I just want to mention that we have discussed this for a more general audience. And in this block, we presented this photo from the Baxter 2020 Frontiers in Integrability that we have these conferences 5 years ago. In Canberra, you see Baxter in the middle and many familiar faces. Here we see Vladimir, we see Murray, we see many people here. Okay, so we can now extend these results, and here I'm presenting the Hamiltonian for n plus m wells here, written in terms of sets of canonical bosons operators A and B. The notation is the same. And these models, they are defined on complete bipartite graphs. And for particular choices of n and m, we recover existing models or we find new ones. For example, for choosing n equals m equals 1, we recover the two-site Boss-Hubbard model that I wrote before. By choosing n2 and m1, we recover the integrable triple well Hamiltonian that I just presented you. By choosing N2 and M2, we obtain the integrable four-well ring model that I showed you before. And by choosing N3 and M1, we obtain an open four-well model. Here we are using the schematic representations that the spheres represent the wells and the bonds indicate the tunneling between the wells. We can also find, for example, a 6-well model by choosing N4 and M2. And an open 6 wells by using N5 and M1. Note, so now an important observation about superintegrability. We have shown that when n is larger than 2 or m is larger than 2, these models, these Hamiltonians, turns out to be superintegrable, which means we have more conserved quantities, independent conserved quantities than degrees of freedom. And the existence of superintegrability allows for the inclusion of additional interaction terms that can break the global symmetry without compromising integrability. And this is very important. This opens many avenues. We can, for example, extend the models to include tunneling terms, keeping integrability. For example, this is an example for N3 and M1, the simplest one. we can construct a super integrable 4 sites in a tetrahedral geometry. You see here this tetrahedral geometry. So you begin with the 3-1 model, you include extra tunnelings, and you arrive to these super integrable models. So now in the next 2 sections, I will discuss applications first of this 2-2 ring, and after of this 3-1 tetrahedral model. Okay, so now moving to section 2, the first applications, I will show how to use the 4 well models in a ring to design Nun states. But what is a Nun state? First of all, let me remind you that a Nun state is an all and nothing superposition of 2 modes. For n particles, it has the form n0 plus a phase 0n. This phase here typically records informations and in applications. And we can find Nun states in many applications: quantum metrology, quantum sensing, quantum information, quantum biology, much more. So now here I want to show how to generate a Nun state, and in addition, how to encode a phase into this Nun state. And our approach is based on the formation of an Uber Nun state first, en route to the final Nun state. What is an Uber Nun state? So to generate an Uber Nun state, we consider first a closed circuit of 4 sides here in the figure. So we have a Fock input state psi 0, M particles on side 1 here in cyan, P particles in side 2 here in blue, and empty sides 3 and 4. So in our protocols, the first step is to create an Uber Nun state, which has this form here. So look in the first line, we have M particles inside 1, 0 particles inside 3, product, P particle inside 2, 0 particles inside 4, plus a phase, 0 particle inside 2, P particles inside 4. Then in the second line, we have basically the same, but now 0 particles inside 1 and M particles inside 3. So basically the Uber Nun can be viewed as an embedding of Nun states within 2 side subsystems. So now what we're going to do, we'll describe 2 protocols to extract a Nun state from an Uber Nun state. For this, we'll consider a model of dipolar bosons confined to 4 wells or sides. And this system has long-range interactions and can be described by the extended Bose-Hubbard model. So this is the extended 4 sides Bose-Hubbard model written here. U0 characterize on-site interactions. Uij, which is equal to Uji, characterize dipole-dipose interactions between bosons at different sites. And J is the coupling for the tunneling between neighboring sites, between sites 1, 2, 1, 4, 2, 3, and 3, 4. So we can show that our integrable 4-well models can be obtained from this model by properly choosing the parameters. So if we use the following choice for the parameters here, the use, this model reduces to the integrable 4-well model that I wrote before. If it's integrable, the model has 4, in this case, the model has 4 modes. So 4 independent conserved quantities are expected because it's integrable. And they are here, the Hamiltonian, the total number of particles, and discharge Q1 and Q2. Okay, from now on, we will be always consider this integrable extended Bose-Hubbard model with the specific Nun state. We have to consider the following. First, as I said, the system is initially in this Fock state MP00. And the second, the system is in the so-called resonant regime, which is achieved for these choices here when U, which is written here, is sufficiently large. So what happens in this case? The energy levels separate into distinct bands, and an effective Hamiltonian age-effective dynamically equivalent to the integrable extended Bose-Hubbard model can be obtained. It can be written in terms of the charts, enabling the derivation of analytical expressions for physical quantities. A very significant feature here in this regime is that M, which is N1 plus N3 particles, can oscillate between sites 1 and 3, which we call subsystem A, and P, which is N2 plus N4 particles, can oscillate between sites 2 and 4 that we call subsystem B. Now I want to describe two protocols that enable the generation of known states. For protocol 1, the outcomes are probabilistic, while for protocol 2, they are deterministic. And both protocols consider the initial state MP00, and both protocols are built around the general time evolution operator U here. H is the integrable extended Bose-Hubbard model. Mu and U are external fields that we apply during a very short time. So here we have the known state generation scheme. In the first line, we have protocol 1. In the second line, protocol 2. On the left, we have the initial state, MP00. So just explaining a bit the figure, here the gradient colors are used to indicate that the state of a site is entangled with the rest of the system. The superpositions are shown here. So we see first the generation in both protocols of an uber-known state and in the end of a known state. These rectangles here represent applied external fields. Okay, let me go a bit more into detail of each protocols. For protocol 1, here is the steps that we implement to arrive at a known state at sites 2 and 4. So this means that we do the following. So the system has an integrable evolution during a time Tm towards an uber-known state. Then we apply a field across sites 2 and 4, doing a short time to mu encoding a phase. Then we measure the number of particles at site 3, and the two possible outcomes are either 0 or m, signifying which of two possible known states results at sites 2 and 4. We can get analytical expression for all steps. For example, for the final step, we find here the first line, if we measure 0 particles at site 3, and the second line, if we measure m particles at site 3. So the states can be recognized as a product of a known states for sites 2, 4, and a Fock state for sites 1 and 3. Now moving to protocol 2, these are the steps that we implement to arrive at a known state at sites 2 and 4. So here we have protocol 2, initial state, then integrable evolution time Tm, apply an external implement a phase pi over 2, again integrable evolution, then apply another external field, doing a short time to mu, encoding a phase. Similar to protocol 1, analytical results can also be obtained. This is for the final state, which can be recognized as a product of a known state for sites 2 and 4, and a Fock state for sites 1 and 3. Okay, what about the fidelities? So we can give numerical simulations for the protocols to find the fidelities. So the fidelities are defined and computed as follows. Here, psi denotes the analytical states obtained using the effective Hamiltonian, and phi denotes the numerically calculated state obtained using the integral extended Bose-Hubbard time evolution. So here we have the protocol, the fidelities for two sets of realistic polar parameters, set 1 in the first horizontal line, set 2 in the second horizontal line. The results for fidelities, first column, protocol 1, second column, protocol 2. This is for initial state 41100. We choose these times here for the application of the external fields. They are very short, and we calculate the time for the integrable evolution analytically. What we see in these tables is that both protocols display high fidelity results greater than 0.9. There is a trade-off between fidelity and total time evolution. The required times to produce the known states are comparable or compatible with typical lifetimes. And an advantage of the protocol is that the time evolution is independent of the total number of particles. In principle, these protocols can also be done in the lab. So I present here a possible trapping scheme to produce the superlattice here by properly using sets of counter-propagating laser beams. Okay, so this was the first application. Let me move now to the next applications, how to use the foresight in a tetrahedral geometry to construct a quantum turntable. So the general idea here is that we will design a quantum turntable that specially transfer entangled states with high fidelity, now in a rotating frame. For this, we will study a system of cold atoms in a tetrahedral geometry that is set to rotate at constant angular frequency omega. The system can be described by the extended Boss-Hubbard model in a rotating frame. So this is a geometric representation of the rotating tetrahedral system. You see here sites 1, 2, and 3 form the triangular basis. The blue arrows shows the dipoles along the z-axis, and the system rotates around z with angular frequency omega in a counterclockwise way. So the model can be written as a particular case of this more general extended Boss-Hubbard model, now in a rotating frame. So the notation is basically the same. So U0 again characterize on-site interactions, Uij characterize dipole-dipole interactions between bosons at different sites, and J is the coupling for the tunneling between different sites. So we have now more tunneling terms than previously. And the last term characterizes the rotation of the system that I will show you later on. So our model is a particular case of this model. Okay, so in our approach, we will combine three basic ingredients. First one, long-range interactions using dipolar atoms. Second ingredient, non-equilibrium phenomena using a rotating frame. Third ingredient, the property of superintegrability, which will be guiding our proposal. We will consider two cases. Case one, non-rotating case. The system is superintegrable. Then, second case, rotating case. We set the system to rotate, superintegrability is broken, but integrability is maintained, which allows us to apply Bethe ansatz. Okay, so let me consider case one, static frame. We have no rotation, so the model is superintegrable in this static frame. So the superintegrable model in a rotating frame can be obtained from this extended Boss-Hubbard model if these conditions are satisfied. So all these conditions have to be obtained, have to be found. In this case, this extended Boss-Hubbard reduces to this Hamiltonian H0 that describes this model of dipolar atoms in this tetrahedral geometry. So this model has 4 degrees of freedom, and we can show that it has 5 independent conserved quantities, so it's superintegrable. Okay, now we set the system to rotate, and in these rotating frames, which means we add this rotation term, minus zeta j, to the Hamiltonian. Now our total Hamiltonian H is H0 minus zeta j. The effect of including this term, which is basically angular momentum in the lattice, is that the superintegrability is broken, but integrability is preserved. Now we have 4 conserved operators here, which will enable us to derive analytical expressions for physical quantities. For example, we have an analytical expression for the expectation values of the populations at sites 1, 2, and 3. This expression here. And from this expression, we can derive the time interval required to particle transfer between consecutive sites, this time tau here. So with this property, we can see that the system can act as a quantum turntable, capable of specially transferring different initial states. So to begin, let me begin with a simple initial state, Fock states. So here I'm presenting you the schematic of this Fock state dynamics on a quantum turntable rotating at constant angular frequency omega. Here the color spheres represent sites with particles. So we have this tetrahedral geometry, and the initial state is the state n000, all particles at site 1. It is rotating, and it evolved to this site 0n00 over the time interval tau. So initial state here, all particles at site 1. Allow the system to evolve during time tau. All the particles are now in the site 2. And the system is rotating, then it goes to site 3 and back to site 1. Now we can also transfer entangled states. We will choose Nun states, but we could use any other entangled states. So here, this infinite symbol implies that we have a Nun state. In the first line, we have one of the components of the Nun states remains fixed at site 4. It's a kind of control site, and the other is transferred across sites 1, 2, and 3, and so on. So initial states, Nun states on sites 1, 4. System evolves during a time period tau. It goes to Nun state at sites 2, 4, and then goes to sites 3, 4, and back to site 1, 4. In the second line, we have the transfer of Nun states prepared initially at sites 1 and 2 here on this plane. So the Nun states at sites 1, 2 are transferred to Nun states at sites 2, 3, 3, 1, and back to 1, 2. We can compute the fidelity of this transfer of states. This is for 19 particles. Numerics in are the markers, and the solid 9 are analytical results obtained by Bethe-Ans. And then we have high fidelity results. So let me go now to some concluding remarks. So more specific in my talk, I have discussed integrable multi-sites or multi-wells tunneling models. As a first application, we show how to generate and encode the phase into a Nun state using the 4 sites in a ring. And as a second application, we show how to use the 4 sites in a tetrahedral geometry to design a quantum turntable. So more general conclusions, we can see that integrable models continue to evolve, showing potential for quantum technologies. We see exactly solved models, past, present, and futures, are windows into the deeper structure of nature. And Rodney-Baxter clarity, elegance, and curiosity remain timeless. I would like to thank my collaborators, John and Phil in Australia, Leandro and Arley in Unipampa, my postdoc Karen, and many students in our institute. This is an old photo from our team in Porto Alegre. We see one of the collaborators. You see John, you see Arley, Leandro, you see Karen, you see Daniel. We have taken a more recent photo in Porto Alegre this year. It was winter, so some students were sick, they didn't come. But you see here Karen, you see Mariana, Pedro, another Pedro, you see Joel, another Pedro, and this is Rodrigo. He is a new professor. He is in our institute, in our group. So our group of integrable models is happily increasing. Okay, thank you very much. Thank you.
Thanks, Angela, for a nice talk. Does anyone have any questions? Anyone can jump in online. They unmute themselves and can ask. Did anyone here have a question in the room?
Hello, Maru.
Yeah.
May I ask a question?
Oh.
Okay. Thank you, Angela, for a wonderful talk. I just want you in your discussion about the transfer of the known state, and you choose 2 known state, then transfer to others. Why not lead to a maximum known state? Why not?
You mean why I choose the Nun state and not any other entangled state? This is the question?
Yeah. To my understanding, if you choose 2 particle from a known state, then you 4 particle interact. Then the entanglement can be changed from one to another 2 particles. But in certain time, maybe the system can become a very, the known state with larger fidelity or larger entanglement. But what is the maximum entangled state?
So we decided to use the Nun state because the Nun state was the one that we generate in the previous application. It was a bit the motivation. But we could, of course, choose another state. This was the motivation. Since we use one model to construct known states, we have the known states, so let us use this one. But we could try to do other entangled states. I know known states are a bit difficult to get in the lab, but because we got it in the previous model, we decided to use this. But we also use other states. For example, the Uber known state we also we can use other entangled states.
Okay, discuss with you later.
See you.
Okay, we should stop there to keep rolling along. So thanks again, Angela, for that.
Thank you.